When you add more GPUs to your AI cluster, you expect linear speed gains. In reality, that expansion often triggers an exponential network failure known as silence. Your compute chips sit idle for hours, not because they are slow, but because the Ethernet switch ASIC managing their traffic has hit a hard limit on buffering and congestion control. Today, we connect this headline to the engineering trade-offs behind cluster reliability and why your scaling strategy might be broken before you even write code. Developers often assume that building a faster AI system is simply a math problem. More GPUs equal faster training times. The reality of modern large-scale clusters tells a different story. Research analyzing 150 million GPU hours across two state-of-the-art data centers reveals that while massive jobs involving thousands of nodes are most vulnerable, they consume the vast majority of resources yet frequently fail due to infrastructure stress rather than dead silicon. The primary culprit for these failures is not a lack of compute power, but network saturation, where switch buffers fill up faster than traffic can be processed. This creates a phenomenon we call silence. It looks like your cluster is running fine, with all lights green and status checks passing. Yet the GPUs are starving for data because they cannot receive gradient updates from their peers in time to keep working. In these environments, adding more hardware actually makes training slower as the probability of network congestion rises exponentially rather than linearly. We see this silence manifesting through a behavior known as link flapping. In clusters with millions of GPUs, an optical connection can appear active and healthy while silently dropping traffic or introducing micro-latencies that force synchronization points to stall. Studies indicate that in massive environments, these link interruptions occur every 48 seconds on average. This is not a rare glitch caused by cosmic rays. It is the new baseline for distributed training reliability at scale. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Current network protocols rely heavily on what we call timeout-and-retry logic. When a packet fails to arrive within a set window, the system waits briefly before asking for it again. However, these standard mechanisms fail to distinguish between a slow connection that will recover and a dead one caused by buffer saturation or thermal variances in the switch, Asic. The result is cascading application-level failures where entire training jobs must restart from checkpoints because the network logic assumes a temporary delay when the link has effectively collapsed for that specific data path. To understand why this happens, we need to look inside the Ethernet switch, Asic itself. Unlike general-purpose switches designed for web traffic or file transfers, AI cluster switches face unique burst patterns where thousands of GPUs attempt to send gradient updates simultaneously at synchronization points. When these bursts arrive faster than the internal buffering capacity can absorb them, the queue overflows like a clogged sink. When that buffer overflows, packets are dropped immediately. The switch does not have enough memory to hold the data while it waits for downstream processing channels to clear up. This forces the GPUs into idle states where they wait indefinitely for gradients that will never arrive until recovery protocols kick in. We call this a gray failure state because the cluster appears alive and responsive, yet functionally paralyzed by invisible congestion collapsing the network fabric from within. The financial cost of ignoring these architectural details is stark. OpenAI reported average GPU utilization dropping to just 32% during massive training runs like GPT-4 due to recovery overheads from these exact types of faults. Meta recorded 419 link interruptions in a single 54-day period while training LL-Llama 3, proving that reliability has become the primary bottleneck rather than raw compute speed. If you treat network failures as mere noise or random anomalies, your scaling strategy will yield diminishing returns and often negative return on investment because every added GPU increases the complexity of failure modes faster than your current topology can handle them. The design trade-off here is clear. You must choose between maximizing raw throughput through bandwidth alone versus prioritizing reliability. Aware architecture with deep buffering capabilities. Standard Ethernet switches optimized for general data center traffic will fail under the specific burst patterns generated by distributed AI training jobs. The best chip in this context is not always the one with the highest theoretical bandwidth, but rather the one engineered to absorb synchronization spikes without dropping packets or triggering cascading timeouts. To improve your cluster's effective training time ratio, you must stop treating network failures as noise and start viewing them as deterministic events at scale. This requires prioritizing switch ASICs that support advanced failure detection mechanisms like Layer 2 reliable link detectors over those with marginally higher raw bandwidth but poor congestion handling logic. You need to tune protocols for the specific burst nature of AI workloads, ensuring that when a bottleneck occurs, it is detected and managed instantly rather than triggering a full job restart. As we move forward in the era of trillion-parameter models, the engineering judgment required shifts from selecting faster silicon to designing resilient topologies where network congestion does not dictate your training velocity. The future of AI infrastructure depends on understanding that silence is not an absence of data, but a presence of failure waiting to happen. If you want to scale effectively, you must build clusters that can withstand the inevitable link flapping and buffer saturation inherent in massive distributed systems without losing momentum or wasting compute cycles on recovery loops. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.